Welcome to this podcast on the laws of motion, specifically forces. Here is what we're talking about. When we talk about a force, we're talking about anything that causes a change in how an object's moving. So the definition of that is that it causes a change in the velocity. And without a force, we can't have an acceleration. We should remember that from last year. When we talk about forces, though, really what matters is what we call the net force. All sorts of different forces can be acting on an object, but really the net force is the only thing that matters. The net force we define as the vector sum of all the forces acting on an object, and we sometimes call it other things like the total force, the resultant force, or an unbalanced force. When we deal with forces, the thing we care about for motion is the net force. When we have zero net force, that means that we have an object whose acceleration is zero and whose velocity is constant. Those three terms are completely synonymous. So if you see any of them in any problems, you know that the other two are also true. Velocity is constant means zero net force means zero acceleration. When we have an object that has a net force equal to zero, we say that that object is in equilibrium. So when an object is in equilibrium, one of two things will occur. Either the object will stay at rest if it is already at rest, or it will continue moving with a constant velocity. Remember, velocity means both direction and magnitude. So direction and speed. It will not change directions, nor will it speed up or slow down if our object has a net force of zero, if the object is in equilibrium. We have some different classifications of forces. The main two are what we call contact forces versus field forces. This is not as important for us to fully appreciate, but the idea is that contact forces you have to physically be touching something, and field forces you can be close to something. So contact force examples that they have is pulling on a spring up here, pulling on a wagon, kicking a football. Those are all contact forces. Field forces, they have a gravitational force, they have an electric force, and then they have a magnetic force. The difference is you don't have to be physically in contact with the object for field force to exist. The other difference is that field forces change as the distance between the objects change. In speaking of forces, we have four main fundamental forces. We've dealt with two of these already in your physics career. We've dealt with gravity and electromagnetism. There are two other ones, the nuclear force and the weak force, or the weak nuclear force and the strong nuclear force. And those two are not as important for this class, but it is a good idea to have an understanding of the fundamental forces. This idea of what's called gut theory, or the grand unification theory, has to do with trying to unify these four forces under one larger umbrella definition of physics. Currently, models that we have unify these three forces, electromagnetic, nuclear, and weak nuclear, but leave out gravity. Gravity is kind of the oddball. So that's what is currently one of the biggest lines of research in the physics community, is looking for these fundamental forces. In this class, a lot of what we're going to be using is using what's what are called spring forces. So when we are trying to find the size of a force, we can use a spring to tell how big that force is. We will get to how the actual spring force is calculated in a little bit here, but remember that there is a value of spring force that is found by the length of stretch that occurs for the spring, and so that is roughly what we use to calibrate our spring scales. So Newton had three laws, and we hopefully remember them, so I'm going to go through them pretty quickly, but I will also expound a little bit on them. Newton's first law is what we call the law of inertia. So if an object is not interacting with any other object, then the definition here that's presented says it's possible to identify a reference frame in which the object has zero acceleration. Now we have to be really careful here. This idea of it's possible to identify a reference frame means that there are other possible reference frames. So what is a reference frame? A reference frame is a location of observation. So for instance, my current reference frame is in my classroom at Madison High School. And in looking around me, I see objects that have zero acceleration based on my current reference frame. But we know that the Earth is rotating around in a circular rotational pattern, right? It itself is rotating, which means that there's no possible way that everything around me has zero acceleration. So we have to be really careful about our reference frames here. But Newton's first law says that if an object doesn't have any interaction with other objects, then it will have zero acceleration in some reference frame. All right. Inertial reference frames, where we can have the law of inertia, is a reference frame that moves with constant velocity relative to an inertial frame. All right, and what does that mean? That means that we can consider really large objects like Earth to be an inertial reference frame because it moves with constant velocity relative to this other frame, right? So our reference frame moves with constant velocity. So the other way that we can say Newton's first law is that if we have no external forces, or if we have no net force, then we have an object that continues to do whatever it was doing before, right? So if it's at rest, it will remain at rest, and if it's in motion, it will continue in motion with a constant velocity. So when we have zero net force, our object will continue with whatever velocity it had before. If that velocity was zero, it will have zero velocity. If that velocity was non-zero, it will have non-zero velocity, but continuous non-zero constant velocity. When we talk about inertia and the inertial reference frame, we're talking about this concept that we call inertia, and inertia ties to what we call mass. When we talk about an object resisting motion, we talk about how much inertia an object has, right? So if you think about the old Bill Nye the Science Guy song, it says inertia is a property of matter. Inertia is a property of matter, and it tells us how difficult that matter is to move. As we found out in our discussion about the Higgs boson, inertia is directly tied to what is theorized to be the Higgs field, right? We have this kind of official, unofficial, unknown definition of the Higgs field, in that mass and inertia are caused by movement through the Higgs field. But this is where we're going to tie it back to what we're talking about here. When we have an object that has inertia, it's the tendency of an object to resist a change in its velocity. So an object that has a high inertia is very resistant to changing its motion. So a train, for instance, it's very hard for me to go down to the Vienna Metro and push a train with my bare hands because that object has a lot of inertia. Whereas the pen that's in my hand right now, it's very easy for me to change its velocity because it does not have much inertia. The difference is mass. We are going to directly measure inertia by measuring an object's mass. So mass is an inherent property of the object. Its unit is kilograms. It's a scalar quantity. There is no negative mass. And it doesn't matter what method we use to measure it, mass exists regardless of that. And mass and weight are two different things. So remember, weight will vary with location. Weight is how much the gravitational force is on an object. Mass is how much that object resists its change in motion. Now, that's important for us to understand because Newton's second law has to deal with mass, not weight, but mass. So Newton's second law says that when we are in an inertial reference frame, the acceleration of the object is directly proportional to the net force and inversely proportional to its mass. So that means that our acceleration increases when we increase our force, our net force specifically, and our acceleration decreases when we increase our mass, right? That's the idea of directly proportional versus inversely proportional. Alternately stated or algebraically stated, it says that net force, right, sum of the forces equals mass times acceleration. Now, net force, again, or sum of the forces, is the net force. That's the one that we really care about. We don't care about what each individual force does on an object. We care about what the net force of the object on the object does. We can also then express this in three different dimensions in terms of its components. The net force in the x direction will cause our acceleration in the x direction. The net force in the y direction will cause our acceleration in the y direction. And the net force in the z direction will cause our acceleration in the z direction. Notice that mass is all the same. It does not have a direction. It's all a scalar quantity. Our unit for force in the SI system is the Newton. The Newton is a kilogram meter per second squared, as we can tell from back here, right? Kilograms, meters per second squared. So the Newton is a kilogram meter per second squared. So the mass is kilograms, acceleration is meters per second squared, so our force unit is the Newton. In the US system, we have the force unit is our pound, and you may or may not have ever known this, but the unit for mass in US systems is the slug, and our acceleration is feet per second squared, so a pound is a slug foot per second squared. All right, there's a conversion between newtons and pounds. It's approximately 4 pounds to 1 newton, approximately, just under, right, 0.225 pounds per 1 newton. So sorry, it's approximately 4 newtons to 1 pound. I misspoke there. So 1 newton is approximately a quarter of a pound. And when we talk about weight, right, then we can use Newton's second law here and say that weight is the amount that gravity pulls us down. So how much is our acceleration as compared to gravity? It's g, right? So the gravitational force, the force with which we are pulled down if gravity is the only force acting on us, i.e. if we're in free fall, is equal to m times g. So the weight of an object is equal to its mass times the acceleration of gravity. The force is always directed toward the center of the Earth because our acceleration due to gravity is always directed toward the center of the Earth, and our magnitude is called the weight, and it's mass times gravity. Because it's dependent on acceleration of gravity, our weight will vary with location. So if we go to the top of Mount Everest, our weight will be less than if we are here in Vienna, Virginia, because acceleration of gravity changes the farther we go away from the center of a planet. We're going to actually skip this slide, take a second to read over it, but it's not going to be very important for this lecture. What will be important is Newton's third law. So we've got Newton's first law, which is inertia, which says that if an object has no net force, it will continue moving in whatever motion it had before. If we have Newton's second law, which says that the net force on an object equals mass times acceleration. And we have Newton's third law, which says that if we have two objects that are interacting, they exert equal but opposite directional forces on each other. So the force from object 1 and object 2 is equal to the force from object 2 on object 1. That's what these notations mean. So F, remember bold is vector, so vector F from 1 to 2, right, exerted by object 1 on object 2, that's our notation. First comes the object that is exerting the force, second comes the object that is being exerted on, is equal in magnitude but opposite in direction to F21. So algebraically, or I guess vector algebraically, this says that vector F12 is equal to negative vector F21. This means that we have the same magnitude because there's no coefficients in front of either of these that are non-1, not 1, or negative 1, but we have a direction shift, right? No negative sign here and a negative sign here. So we have Newton's third law, which says that an object that exerts a force on another object has the same amount of force exerted back onto it. So we can say it a few different ways. Forces always occur in pairs, so you can't exert a force on another object without that other object exerting a force on you. We cannot have a force existing in isolation. And we have this thing called action-reaction forces. So the action force is the force that we initially observe, so this would be me pushing down on the table. And the reaction force would be the reaction coming back onto me, so that would be the table pushing back onto me. Take a second right now, push your hand down on the table, and you can feel that you know you're pushing down, and the table pushes back up on you. You're pushing down is the action force, the table pushing up is the reaction force. You are the initiator of the force. All right, but it doesn't really matter which one's which. The result is that they are equal in magnitude and opposite in direction. And you have to make sure that your action-reaction forces are between just two objects. Just two objects. So here's an example or a visualization of this. Right? If we have two objects, we have a gravitational force maybe between these two objects. We don't know what kind of force this is. But object 1 here is exerting a force on object 2, that's this, F12, F from 1 onto 2. So object 1, the green object, is exerting a force onto object 2, the orange object, with this magnitude of size and this direction, right? So this is a gravitational force pulling this way. And Newton's third law says that this force, F21, must also exist and point the opposite direction but be exactly the same size. So if we were to measure the length here and we were to measure the length here, we would get the exact same length. All right, and here's our final piece to this presentation here today. Here's an action-reaction system. A normal force, right, the force that the table is exerting on the monitor is the reaction force of the monitor pushing down on the table. So as we push this monitor, as we put this monitor on the table, gravity pulls the monitor down. In turn, the monitor pushes against the table, and the table then pushes back up on the monitor, which is the action-reaction force. So we have a force going up from the table onto the monitor, which is caused by the force going down from the monitor onto the table. Now, we also have an action-reaction force in the gravitational pull from the monitor, or sorry, on the monitor from the Earth, and there's also an equal but opposite directional gravitational pull from the monitor onto the Earth, right? So we have action-reaction pair number one is this force here, paired with this force here, and action-reaction force number two, pair force is number two, is this being pulled down here compared to this being pulled up here. Yes, every object that is pulled down by the Earth is also pulling up on the Earth itself. And you can think about in just 1 or 2 seconds why we don't see any reaction, any acceleration from the Earth as a result of our pulling back up. That's all we got today. We're going to talk more and more about Newton's three laws next time in class, and we will start delving into free body diagrams.